In this lecture, we will be discussing about the design of stator slots. So, in the stator design, there are two parts: design of stator lamination and design of stator winding. So, we have already discussed about the design of stator winding. Now, we have to design the stator lamination. So, designing a stator lamination means to decide how many number of slots have to be punched in that particular lamination and what is the size required for the slot. Okay, so before going to that, let us see what are the factors affecting the choice of number of stator slots. Okay, so first one is tooth pulsation loss. So what is tooth pulsation loss? So as the name indicates, it is the loss due to a pulsating flux. A loss produced in the tooth due to a pulsating or varying flux. So, tooth pulsation loss is produced due to varying flux in the air gap. Now, what is the reason for this variation of flux? It is due to the non-uniformity of the air gap. So, if the air gap is uniform, the flux will remain uniform or constant. But if the air gap is non-uniform, then flux will vary or it will pulsate. Now, what is the reason for this non-uniformity of air gap? And it is slotting. So, the stator surface is not smooth. It consists of slots and teeth. So, due to this non-uniformity of the stator surface or due to this slotting, air gap becomes non-uniform and flux becomes non-uniform. So, what we have to do in order to reduce the tooth pulsation loss? So, tooth pulsation loss is due to non-uniformity. So, in order to reduce this loss, we have to reduce that non-uniformity. Okay. Now, see these diagrams. So, here we have a large number of narrow slots and here we have small number of wide slots. Okay. In which case the air gap is uniform, more uniform, or it is likely uniform. So we can see in this case we can say the air gap is almost uniform, but here the non-uniformity is more. See, the air gap is very much non-uniform here. So we can reduce that non-uniformity by using large number of narrow slots. So if we use large number of narrow slots, non-uniformity of the air gap can be reduced and hence tooth pulsation loss can be reduced. So that is the first factor. Now moving on to the second one. That is leakage reactance. The second point is leakage reactance. Suppose we are using a large number of slots, then we have to separately insulate each of the slots and hence width of the insulation increases. So, if there is more insulation present in the machine, then flux leakage will be less. Leakage flux decreases, and if leakage flux decreases, leakage reactance will decrease. Leakage flux decreases means leakage reactance decreases. So, we have already discussed about the effect of reduction in leakage reactance and increase in leakage reactance while we were discussing about the choice of B average and AC. Okay. If leakage reactance decreases, this current ISN decreases. This is a parameter in the circle diagram. The short circuit current with normal voltage applied to the primary. So, when XL decreases, ISN increases, and when this increases, the diameter of the circle diagram increases. So, we have already seen those factors already while discussing about the choice of B average and AC. Let me show it again. Okay. So, this is the circle diagram corresponding to two different cases. So, here this is ISN and here an increased value of ISN is shown. So, if we are referring to both these circle diagrams, we can see that with increased value of ISN, the diameter of the circle diagram has increased. So diameter of the circle diagram increases means maximum power output from that machine will increase. That means overload capacity of the machine increases. So with the use of larger number of slots, overload capacity increases. So number of slots increases means insulation increases, leakage flux decreases, leakage reactance decreases. As a result, ISN increases, diameter of the circle diagram increases, and overload capacity of the machine increases. Okay. Now the third factor that we have to consider is the ventilation. So suppose we are using a large number of slots. So number of slots increases means width of the tooth decreases. Okay. So when width of the tooth decreases, the tooth will become weak. So as it is weak, we have to provide a separate support for the tooth. And the teeth are actually supported at the ventilating duct. We will provide the support for the tooth at the ventilating duct. And this will obstruct ventilation. So there will be an obstruction to ventilation when a large number of slots are used. The fourth point is the magnetizing current and iron loss. So suppose there are a large number of slots, then width of the tooth will be less. So width of the tooth is less means area of the tooth is less and flux density in the tooth will increase. Flux density is flux divided by area. When area decreases, flux density will increase. That means the tooth may get saturated. It will lead to tooth saturation. So magnetizing current will increase, and also when the flux density increases, iron loss also will increase. So with larger number of slots, magnetizing current and iron loss increases. And the last point is cost, which is very easy. Okay, easy to remember. This point is very easy to remember. So large number of slots means that much number of slots have to be punched in that particular lamination. So labor cost for punching the lamination increases. With larger number of slots, the labor cost for punching the lamination is more. So these are the various factors that affect the choice of number of stator slots. Okay. Now we have to choose the exact number of stator slots. So till now we have discussed about the various factors that are affecting the selection of the number of stator slots. Now we should know how to select the exact number of stator slots. And same as we have done in DC machines, here also slots are chosen on the basis of slot pitch. And while choosing the slots, always keep in mind that the slots per pole per phase, that is Q, the quantity Q, slots per pole per phase should not be less than 2. It should have a minimum value of 2. And in most of the cases, okay, keep this in mind, in most of the cases we are using this value 3, subjected to other constraints, and it is more likely to be 3. So, and now what is the range of slot pitch? In DC machines we have fixed the number of slots on the basis of slot pitch. So here what is the value of slot pitch? See, for large machines the slot pitch should be in the range 15 to 25 mm. For large machine, slot pitch is in the range 15 mm to 25 mm. And for small machines, the slot pitch can be less than 15 mm. There is no problem even if it is less than 15 mm. Okay, and what is the equation for slot pitch? Slot pitch is pi d, that is perimeter, circumference of the stator divided by number of stator slots. Circumference of the stator divided by number of slots will give the distance between two adjacent slots, that is the slot pitch. Okay. So in order to get the distance between two adjacent slots, we have to divide the total circumference by the number of slots. Then we will get the slot pitch. This is the slot pitch. This is the slot pitch, distance between two adjacent slots. This is the slot pitch. Okay. So circumference of the machine divided by number of slots will give us the slot pitch. Equation is pi d by SS. SS is the number of stator slots. So substitute the value, this range, in this equation, and we can correspondingly calculate the total number of stator slots. Now, the total number of stator conductors can be calculated as 6 times Ts, where Ts is the stator turns per phase. We have already calculated this. Stator turns per phase. Ts denotes stator turns per phase. So number of turns for all the 3 phases becomes Ts into 3, and number of conductors is number of turns into 2. So 3 into 2 into Ts will give the total number of conductors. 6 Ts. Have we got this? Ts means stator turns per phase, corresponding to one phase. So corresponding to all the 3 phases, there are 3 Ts number of turns. So 3 Ts turns. One turn means 2 conductors. So into 2 will give us the total number of conductors, 6 Ts. Now we have the total number of conductors, and from here we can calculate the number of stator slots. So number of conductors per slot. How many conductors are there in one slot? Conductors per slot is equal to total conductors divided by total number of slots. So this is how we can fix the number of stator slots. So now one more is there. After calculating the number of stator slots, we have to choose the area of the stator slots. And this is how area of the stator slot is calculated. See, area of stator slots. Area of stator slot is equal to copper area per slot divided by copper space factor. Okay. So area of the stator slot. How much area has to be provided for a particular slot? It depends on the number of conductors to be accommodated in that particular slot. അല്ലേ, ഒരു സ്ലോട്ടിൻ്റെ ഏരിയ ചൂസ് ചെയ്യുന്നത് ആ സ്ലോട്ടിനകത്ത് എത്ര കണ്ടക്ടർ വെക്കണം എന്നുള്ളതിനനുസരിച്ചായിരിക്കും. ബട്ട് ദ ഏരിയ ഓഫ് ദി സ്റ്റേറ്റർ സ്ലോട്ട് ഷുഡ് നോട്ട് ബി ഈക്വൽ ടു ദ ടോട്ടൽ ഏരിയ ഓഫ് കണ്ടക്ടേഴ്സ് ടു ബി പ്ലേസ്ഡ് ഇൻ ദാറ്റ്. അല്ലേ, എത്ര കണ്ടക്ടർ വെക്കണം അത്രയും മാത്രം ഏരിയ അല്ല, അതിനേക്കാളും കുറച്ച് ഏരിയ കൂടുതൽ വേണം നമ്മൾ പ്രൊവൈഡ് ചെയ്യാൻ. ഓക്കെ, സം ക്ലിയറൻസ് ഷുഡ് ഓൾസോ ബി പ്രൊവൈഡഡ് because we have to provide the insulation, etc. So the total area of the slot should be somewhat greater than the total area of the conductors that are to be accommodated in that particular slot. So area of stator slot is calculated as copper area per slot. Copper area per slot means total conductor area in a particular slot. So how will you calculate that? Total conductor area or total copper area in a particular slot is number of conductors in that particular slot. We have denoted it as ZSS, conductors per slot, into area of one conductor. This will give the total copper area or the total conductor area in one particular slot. So that divided by space factor will give us the area of the stator slot. Space factor is a constant which is less than 1. So when this is divided by space factor, we will get an area which is higher than this term. Okay, then we can provide the insulation also. So area of stator slot is equal to copper area per slot, that is total conductor area in a particular slot divided by space factor. Conductor area is calculated as number of conductors per slot into area of one conductor. So this is how the slots can be designed for an induction machine.